last class we were discussing about working principle of the lock-in amplifier, and lock-in amplifier is used mainly to remove the noise, and also it is used to separate out in phase and out of phase components. So, we had shown in the previous lecture that how the noise is removed by means of averaging. So, we had shown that we can have switches, with the use of 4 switches we had shown how to remove the noise which is actually signal which is buried in the noise. So, we had shown last time that we had these switches so, we have these switches S1, S2, S3 and S4. So, we have the difference amplifier here. So, when the signal here going positive and negative. So, when the signal is positive here, when the signal is positive, you want the output to be positive, then at that time switch on S3, switch off S4. So, that whatever signal is coming, it comes here. At that time we switch on S2. So, at positive when this signal is positive, S2 on, S1 off, and then S3 on and S4 off. So, the positive signal appears as it is, and then we do the reverse of this when signal is negative. When the signal input is negative, then we want whatever signal that is coming here, that is to be applied here and inverted and is put here. So, that inverted become again positive. For that we switch on S1, we make S1 on, S2 off, S3 off, S4 on. So, the minus voltage whatever is coming here, that appears here and it is getting inverted, and the inverted voltage become again positive at the output. So, you will get a signal like this. If noise is there, noise which is positive or negative, whatever was there at that time, that appears as it is, because these switches are actually they are not like diode, they allow both positive as well as negative values together. But we are operating this, we are allowing the signal to go when the signal is minus. At that time whatever signal the noise is there which is positive or negative, that also comes and appearing at the output. So, because of that you will get output which contains typically signal which are actually always put at positive side, and the noise whatever was there which may be positive or negative. So, that is how it appears at the output, and net result is if the output is filtered, then that will have only the DC voltage proportional to noise. So, VDC is proportional to noise, and this is the time constant we had to select such that time constant of this RC time constant much larger than the noise frequency that we are encountering, probably the lowest noise frequency lowest noise frequency will be compared with this RC time constant. So, by means of averaging noise is removed. For this to be effective, we need RC time constant much larger than lowest noise frequency. So, this is how the lock-in amplifier works. Let us see before getting into the actual lock-in design, we will see what is the other use of the lock-in amplifier. Other use of the lock-in amplifier is separating out the in phase and out of phase component. That is required at many places because in phase and out of phase component get mixed up if we have, for example, resistance and capacitor together, or inductor and resistance together, or both R L C R combined, also can have in phase and out of phase component mixed together. So, it is essential to separate out for example, R and C in RC circuit, that is what is the value of resistance, what is the value of capacitance can be separately find out using the lock-in principle. So, let us see what is the basic concept involved in separating out the in phase and out of phase component. So, lock-in amplifier to separate out in phase and out of phase components. Now, because if I have, for example, AC source, and then if we have RC circuit, for example, I can have R and then C. Now, if I look at the current through this current and this voltage. So, the voltage at this point and then the current through this, they will have a phase shift. If it had been a pure resistance, then the current and voltage would have been in phase. Now, there will be a phase shift between this current and this voltage. In this case, current would be leading and the voltage will be lacking actually. So, you will have for example, this is voltage at 0, we will have current leading. So, we will have already the current actually leading and the current reaches maximum at this point. You have, for example, in 90-degree comments you will have this, and then this actually the peak occurs nearly at 0 point. So, you have a phase shift. Of course, the phase shift need not be 90-degree. So, here the current leads the voltage. Now, if I want to measure the capacitor and resistance separately, then I should it is possible to separate out the in phase and out of phase components. This I can reconstruct this by superimposing two ways, that is the resistance gives you in phase component which is in phase with the voltage, and then the capacitor gives me capacitor gives me the current which is 90-degree. This is current due to resistance, this is current due to resistance. The capacitor current will be leading 90-degree. So, you will have at this point the redraw the. So, you will have a resistance component gives this kind of current, this is R, and then the capacitor part actually will have a leading amplitude. So, current would be maximum here and then it comes back to 0 in case of, and then at 0 it goes minus maximum, and again at peak it comes to 0. So, you will have this is actually due to current due to capacitance, this is current due to resistance. We can superimpose this and get the resultant waveform, resultant current waveform, that is what happens. So, one, if I can separate out the in phase and out of phase component, then it is possible to measure the resistance and capacitance separately. For example, we had discussed earlier about the use of ratio transformer bridge. So, wherein we had transformer like this, and then we had secondary with tapping, and then if the capacitor to be measured, we put the capacitor here, and then we connected the detector here. This I had explained earlier that how this avoids various stray capacitances. Now we see how the lock-in amplifier can be effectively used in this case. So this is a ratio transformer bridge. The ratio transformer bridge for capacitance measurement. Now assume that this in actual balancing, we will say, for example, this is a unknown capacitor C sample and this is a known capacitor C. Then we have this Vs here, and then V the voltage, that is the with respect to ground, what is the voltage here, what is the voltage here. Actual working principle is that the voltage this V actually drives the current like this. This Vs actually drives the current to the detector like this, and the V drives the opposite current in the reverse direction. If these two currents, current given by this and the current given by this are equal, then you will get a null at the detector. So by knowing V by Vs, one can find the ratio of the actual balancing point, that is the current through Cs will be given by Vs, the current through Cs is given by Vs into Cs omega, and that should be equal to V into C omega should be given. So that comes out Cs by C comes out to be V by Vs. So the once I know if I know C, the known value the C is this is known value, if I know the value of C and Vs is and V is known. So C is known, in this case C is known and Vs is known. So Cs can be determined. Now for in this case a simple detector will do, but unfortunately in real life these capacitors may not be ideal capacitors. The capacitors may have its own resistance. So let us see the real life situation, that we have AC voltage applied here, and then we had the ratio transformer, this is a center tap, then you have this resistance, assume that this is having a resistance here. Then we will have another component, and this resistance also to be introduced. Now if this is a sample and then this is Rs and this is C and then this is R. Now the detector will balance the detector current is due to both R and C, due to both R and C. Now it will balance only if both resistive component and the capacitive component equally balances out. Now that would be difficult, because if you see that if I vary this one, it varies both this voltage, for example if I have Vs and V. So if I vary the center tap, then Vs changes, V also changes, but then it can balance only one component, that is either C or R, not both. So if I have a detector, assume that if I have a detector which detects only in phase component, in phase with the applied voltage, for example if this is the applied voltage, if I have a detector which is sensitive to detect only the component which is in phase with this, then at that time I can balance only R. By varying this I can balance R. Suppose I keep this detector which is sensitive to 90 degree out of phase, assume that detects only a 90 degree out of phase component with respect to the applied signal, then I can balance C capacitance by adjusting this. So, one can balance separately RS and R. In this case, if assume that RS, the leakage, the shunt resistance RS and R are very high. If it is very small, then we will have other set of problem, and we have to modify this one. There are ratio transformer bridges called double ratio transformer bridge and so on. But we will not get into this. Here we assume RS and R are very large, but still it is a considerable amount when capacitors are very small. So, under this assumption, let us see how the lock-in amplifier can be utilized here to balance the bridge, that is to separate out in phase and out of phase components. So, assuming RS and R is large, we can balance the bridge, for, for resistance and capacitance separately. Now, first to balance resistance, make D sensitive to in phase component. There is in phase compared to the applied voltage, in phase compared to the applied voltage, that is Vs or V. Similarly, to balance the capacitance, make D sensitive to 90 degree out of phase component. So, then one can balance out resistance and capacitance separately. So, if I keep this one sensitive to 90 degree out of phase component with respect to the Vs R with respect to the input voltage, then this I can vary the center tap to balance capacitance alone. It will ignore the resistance part. Resistance part play a very less role, because this detector is not sensitive to in phase component. So, for example, if I want to measure capacitance, then make it sensitive to out of phase component and then vary this. So, you will get capacitance measured, then make this D sensitive to in phase component, now balance and get the resistance value. So, this detector now becomes basically lock-in amplifier. This detector can be a lock-in amplifier. So, let us see how to make it sensitive for in phase and out of phase component. The D is the detector T is now lock-in amplifier. So, let us see how the lock-in amplifier is sensitive to in phase and out of phase component. So, how lock-in amplifier is sensitive to 90 degree phase component. Now, this can be achieved in the following manner, like we are seeing the switches. Now, I take a simple case that I have a signal source here, then you have the switch here, then assume that we had input here, assume that I put the source here, connect the signal at the output. Now, we have to operate this switch. Now, assume that I put here the analog switch or assume that this is analog switch, and then I give a gate signal to this to make it on or off. For example, if I apply a gate voltage, assume it is on and it is off when the gate voltage is 0. So, if the input signal and the gate signal, suppose if I have a input signal like this, then let me have a phase shifter here. We have a phase shifter here, which is 90-degree phase shifter. So, basically 90-degree phase shifter I have, and then I take the output. So, this will be the input signal here, and the output here will be 90-degree phase shifted. That means, when it is 0, it is actually high, when it is 0, the input is high, and then when it is high, okay, I will put the points here. So, you get so we start here, and then it becomes this leading phase. So, we will have signal 0 degree, you have 90-degree phase shift already. Then it slowly comes back to 0 degree, you have to have 90-degree phase shift, yes, and then comes back to 0 here, then goes back to minus 90 at this point, comes to 0 again at this point. So, you will have a 90-degree phase shifted component coming at this point. So, you will have the signal completed like this. So, output is phase shifted at this point, and then you get a phase shifted output. Now, what I do is I will square this waveform and offer to the switch actually. So, what I do is that I will have a signal, then I will give it to the switch. For example, I will put a bilateral FET switch, then I will have the voltage here. Now, this I will have a 90-degree phase shifter, 90-degree phase shift. Then this I put a squarer, which converts into a square wave. So, you will get a square wave which is 90-degree phase shifted compared to the sine wave. So, we will have the two waves. If you see, that is the input sine wave like this, and then you will have the output which is actually phase shifted and squared. So, you will have we will have the change occurs at this point, again the waveform changes at this point. This is a 90-degree phase shifted wave. So, you will have that is the voltage that you get, 90-degree phase shifted square wave. This 90-degree phase shifted square wave is given to the switch. So, for example, if then if I look at the voltage at this point, I will get I will be getting the sine wave like this, because whenever it is on, the output is coming. So, you will have the voltage comes like this, then you get no voltage. Then other half, assume that it is negative side, it is completely off. So, during the positive cycle, that you will get the signal. So, other half you will not be having the signal. So, you will have a signal coming out like this at the output. So, if you see this, half the sine wave is coming, other half is this is lost, it is not there, the switch is not allowing the other half to come. So, you will have signal at this point, positive half of positive, and half of negative will be coming here. So, suppose if I put RC network at this point, for example, I put on RC network at this point, then I will get a 0 volt. I will get a 0 volt. So, this is because this the whatever voltage is applied here 90-degree phase shifted, and then we are switching. So, you will get of the sine wave, that is you will get the voltage of this part. For example, in this case I can show you separately now with assume I have a sine wave like this, then I have a square wave which is like this. Then you will have, now if I operate this, then I will get only this waveform alone will be coming here. So, you will get the output when the switch has and that is what it turns out. So, when it is average route, the average value is 0. That means, now the signal here this and this are if the 90-degree out of phase. So, there is no so the output is actually 0. Suppose if I make it without phase shift, for example, if I without phase shift if I had switched, then the signal would have been like this without phase shift, without phase shifter. Then the signal would have been like this, and the square wave would have been like this. The next wave would have been like this. Then output of the after the if it passed the switch, then you would have got the signal, the positive half cycle, and the negative is not coming, again the positive half cycle would have come. Average is not 0. Average is not 0. That means you would have got the signal. That means if I make it the switch, if I make the switch such that if this and this are in phase, if the input and this are in phase, then I will get maximum voltage. If this input voltage and the gate voltage are 90-degree phase shifted, then I will get a 0 volt, average value as a 0 volt. Now, using this one can separate out in phase and out of phase component, because if it is a capacitive component, then you would have got some phase shift. For example, in the lock-in amplifier case, that we had both capacitor and resistance here. So, we have the here lock-in amplifier is used. Now, we connect this. Now, the lock-in amplifier switches we have discussed. Suppose if I make sure that I take this as a input voltage, I take this voltage, assume this is grounded, I take this voltage and then I square it up, I put a squarer, then I will get a signal which is square wave, that is in phase with the applied voltage. This square wave is in phase with applied voltage. Now, if I lock-in amplifier switches are switched using this square wave, that is in phase square wave. Now, the lock-in will be sensitive only for the resistive component, because the resistive component current will be flowing, and lock-in output the average output of the lock-in amplifier will not be 0, and then you will have a resistive component. Now, we know the capacitive current what that is coming through this, that is the capacitive current that is coming here is a 90-degree out of phase component. This current and this current both are opposite, that this goes like this and this current goes like this. They are actually opposite, but these currents actually are 90-degree out of phase. So, but we are switching that with the in phase signal. So, the 90-degree out of phase current would have produced 0 output. So, if I switch this, for example, if the lock-in amplifier amplifier is switched with the in phase component, in phase square wave, a square wave, then only resistance current will produce output, the capacitance to the capacitance current will not produce any output. Similarly, if I switch if I introduce a phase shift, 90-degree phase shift and switch, then the capacitance component will be sensitive and resistance component will not be sensitive. That is, what you can do is that you have a the ratio transformer. Now, you have this resistance and capacitance. Now, what you do is you take this signal and have a 90-degree phase shift, then I have a squarer, then I switch this to lock-in amplifier. No, I switch the lock-in amplifier with this squarer. Now, if I do this, now resistance component will not be sensitive, only capacitor component will be sensitive. Now, lock-in is sensitive only to capacitors, capacitance change and not for resistance change. Not for resistance change. This is important. Because of this, one can separately balance out resistance and capacitance. That is, make it first introduce a 90-degree phase shift, then it is sensitive for capacitance. So, now I adjust this and balance the capacitance, then I remove the 90-degree phase shifter, then I balance it, that balance is given for resistance. Of course, this works only when resistance value is very high. There are other issues involved when the resistance is not very high. When the resistance value is low, then you have other problems. So, as long as the resistance is high, this works well. So, lock-in amplifier that way can remove both the noise, as well as it is capable of separating out in phase and out of phase component. So, let us see how to design the lock-in amplifier, because now we have seen the theory that is behind the lock-in amplifier. Now, let us see how to design a lock-in amplifier. So, obviously, the we have a sine wave as a input excitation that is required. So, we take this capacitance measurement ratio transformer bridge only as an our example, and then design the lock-in. So, what you do is we will take the output of the bridge, that is the output of the detector as an input to the lock-in amplifier. So, the obviously the input signal we have to get is this input is given here. Then this contains signal plus noise, and also we are it is necessary to separate out the in phase and out of phase components. Then I will have obviously amplifier, so that even the small signal is picked up. So, maybe I need few stages of amplification, so that there is not much phase shift is involved. So, you will have a wide bandwidth amplifiers we have, and we amplified the signal. Then the if we take the bridge here, that the bridge consists of the primary and then the two secondaries. I think I draw it at this point. I draw it at the bottom. So, we will have the essentially this is the input to this, and this is the excitation signal, and that is grounded. Now, what I do is I had to produce a phase shift and then the switching network. So, the switches can be what we had earlier, that we will have the amplifier put here. So, we have the switches S4. Now, we have generate a signal which is actually which is either in phase with the input or 90 degree out of phase with the input. That input signal is now this is our reference signal, this is the reference signal. Now, with respect to that, we have to switch them, assume there is no phase shift introduced in this and in this. And if that is the case, what can be done is that I can take this, for example, if I want to measure the in phase component, then I can take this, then square it off and give, but then I also want to have 90 degree phase shifted component. So, I can have a phase shifter here which is 90 degree phase shifter input, then the output is here. Now, what I do is I can have a switch here which either selects in phase component or it selects one of them 90 degree out of phase component. Then this okay, I will redraw this. That I can select either in phase or out of phase component. Take this output, that is I have a provision to either to switch to this or switch to this. Then I take this output. This output is given to a squarer. The squarer can be a simple comparator, for example. So, whenever this is high, for example, this can be used to switch switch on. When it is low, it can be used to switch off. So, I can generate one more signal which is giving me another phase reversal. So, this I can give this and give to the ground. So, now I will have two square wave signals, both are 180 degree out of phase. So, you will have square wave 1 and square wave 2 which are 180 degree out of phase, that can be used to switch these 4 switches. For example, one can be given to S1. If S1 is on, we want at the same time S4 also to be on, and the 2 can be given to H2 can be given to S3. When S3 on, we want S2 also should be on. So, we can connect these to the gates of this, that is the this output can be given to gate of S1 and S4, and this output can be given to gate of S3 and S2. So, if it is for example, if I want to measure in phase component, then I connect this switch, for example, this switch I call it as S. So, connect the switch S to position, say I will put the position actually 1 here, 2 for in phase measurement. In phase measurement connect in phase measurement connect S to 0.2. Now, when it is in phase, you will have output here positive. So, that will make this, there is a small change here, that I will make this S3, that is if it is positive, then S3 to be on, and then S2 should be on. So, when it is in phase component, when it comes in phase, then this will be high during positive half cycle, that will make S3 on and S2 on, and at that time this will be off. So, we will go to this one S4, this is connected to S4 and S1. S4. So, at that time when say that is S3 and S2 will be on for in phase measurement, then connect to point S2, then now S3 and S2 will be on, S3 and S2 will be on, that will produce a positive output. So, output V naught, so output V naught will be positive, and of course, here S4 comma S1 off. That means you will get in phase component now, because we have put at position 1, that is at point 2. So, you got in phase component, and then switching is done for the incoming wave which is in phase. So, you will get output which is positive half cycles, and output is now sensitive for in phase component, that is output is now sensitive for resistance measurement. Now, for measure capacitance, that is this measures this measures the resistance, that is it measures the in phase component. Now, to measure the capacitance, connect switch S to position 1, connect switch S to position 1. That is what you do is that we will now connect to position 1 here. So, the signal what you are getting here is 90 degree out of phase. So, the square waves also will be 90 degree out of phase with respect to the input signal, that is with respect to this. So, here whatever signal that is being switched, whatever that is switched will be 90 degree out of phase with respect to incoming wave. So, the output now what you get will be say 90 degree phase shifted, or it will be in phase for capacitance current. So, now it will be sensitive for capacitance current, was like now now the bridge is sensitive for capacitance. Bridge is sensitive for capacitance. So, the output of the lock-in amplifier will give only the capacitance component, and we will have, whereas if it is average, we will get only capacitance component, and also it will be removed of the noise. So, if you look at the output now, we filter it from the output of the switching stage, that you will get this output. So, Vx will be without noise, and also it output can be selected for in phase or out of phase. Now, this is the it is a very important instrument as far as signal processing is concerned, particularly when signal is buried in noise, one can remove the noise, and as well we can separate out in phase and out of phase component using the lock-in amplifier. So, using lock-in amplifier, uh, the two things can be done. One, separate out the in phase and out of phase component, separate out the in phase and out of phase component. To remove the noise, from the signal. So, that is why the earlier days lock-in was very popular. Even today lock-in amplifier is very popular, but this also can be done digitally. For example, the before discussing the other use of the lock-in amplifier, I just give you the circuit diagram of the phase shifter, so that one can one can design the full lock-in amplifier as it is. So, for example, the phase shifter circuit can be like this. The phase shifter circuit, the input for example equal resistance support, and for example R filter and C filter. By varying either RF or CF, one can vary the phase shift, vary the RF to vary the phase shift, between input and output. Now, this phase shifter, this can give maximum of 180 degree phase shift. So, one can set whatever phase shift required in this stage. For example, you can select for 90 degree phase shift, the resistance can be selected, so that and the capacity can be set, so that 90 degree phase shift appears at the output. So, for 90 degree phase shift, for 90 degree phase shift, select suitable RF and CF. The phase shift of course depends upon the frequency, and if more than 180 degree phase shift required, the two stages can be added together. So, one can have normally two stages of phase shift. For example, you can have which actually can give you maximum of 180 degree 360 degree phase shift considering both the stages. So, one can get between the input and output, the input and then the output, you can have 180 degree phase shift is possible. Uh, maximum of 360 degree phase shift possible considering both the stages. Each stage gives you 180 degree out of phase. So, considering both the stages. So, normally we need to have a additional phase shifter other than the 90 degree phase shift that what we had shown here. We have shown only 90 degree phase shifter. In addition to this 90 degree phase shifter, we have to have additional phase shifter required to compensate the phase shift that occurred in these stages, because in actual case there will be a phase shift here, there will be some phase shift here and there will be some phase shift here, and simply by shifting 90 degree exactly you are not able to switch in phase and out of phase. So, in actual Lock-in amplifier we need to introduce additional phase shifter here in this stage, so that one can have this phase shift will be equal to this, so that one able to get in phase and out of phase component accurately. So, if you look at the total Lock-in amplifier, it looks like this, that you have a series of amplifiers at the input. If we have a voltage follower and then the amplifier stages, then you will have the switches which we had seen earlier. Then you had this. So, you have the plus minus the switches, then this input signal whatever was coming, that reference signal was the same reference signal was taken, the reference voltage, and that actually you will have a 90 degree phase shifter, 90 degree phase shifter with the provision for selecting in phase and out of phase component. Then this might need additional phase shifter, additional phase shifter, and then the squarer, then inverter, that this inverted output is for 2 switches and this is for 2 switches. So, you have S1, S2, S3 and then you have one more switch here S4. So, this supposed to be given to S1 means then S1 is on, then it also has to go to S4 and then this has to go to S3 and S2. So, one can select in phase and out of phase component by one can say this is 0 and 90 degree, 0 and 90 degree. So, if you want to measure in phase component, then select the 0 degree position and then introduce a phase shift. That phase shift will be equal to phase shift introduced by these amplifiers. So, you got at this point see this sine wave which is in phase with the signal here. Now, you square it up, make it a square wave, so that the switches are switched, and then to produce a reverse square wave, then invert it and then again get a square wave, and these outputs can be connected to these switches. Now, that completes the lock-in amplifier design, because I had already given you how the phase shifter to be made and how the squarer and inverter to be made. Only thing is that these switches are not discussed in detail. These switches are analog switches which is available. For example, the typical switches are CD4016, which is a analog bilateral switch which allows both positive and negative analog voltages to pass through. So, one can configure this using a plus minus power supply, so that these switches also can be working properly. So, for use analog switches for CD46, that will make the lock-in amplifier complete, and then of course, the output should be connected through a time constant, this RC. The time constant must be selected. Larger the time constant, the better the noise rejection. So, one can have various values of RC, and if necessary this output also can be taken out using a voltage follower circuit. Now, in this lock-in amplifier, of course, you are getting output voltage which is not sensitive to noise, in the sense signal which is buried in the noise can be extracted. Of course, the output voltage is only DC, the original signal is not retained as it is. Of course, we were able to separate out in phase and out of phase component, and we are able to remove the noise, but the original sine wave is lost, the output we do not get the original sine wave. There is another device which is called Boxcar integrator, which was earlier days used, which can even give back the original signal wave shape. So, that issues we will discuss in the next class before getting into other issues of AC amplifier. Thank you.